Hello and welcome. Today we're going to do acid-base reactions, another example of double displacement. So acid-base, you're going to need an acid that is an H plus source, a proton source, and then our bases today will be hydroxide OH minus sources. All right, so you're going to have an acid and then you'll have a base. The acid, it could be a strong acid or it could be a weak acid. And then for our bases, we'll just limit it to hydroxides today. So if you have an H plus and OH minus, what are you going to make? You're going to make water, a liquid, and then you'll make some sort of ionic compound. That ionic compound might be a solid, precipitate, it might be aqueous. So we'll use solubility rules like we talked about in the previous video to figure out some of that. So if you're doing these in real life or in the lab, you're going to notice, especially at higher concentrations, these acid-base reactions do get quite warm. All right, that's a good way of knowing that you've done this exothermic reaction of the formation of a very stable water molecule. All right, so enough talk. Let's go ahead and talk about the steps. Just like I said in the previous video, 2 steps. Number 1, figure out the products, do some charge balance. And then number 2 is where you actually balance the equation, also known as mass balance. Do not try to balance the equation until you've figured out the products. Super important. Once you have determined the products and you're in the balancing phase of writing your chemical equation, please remember that you can change coefficients. Yes to changing coefficients, but we do not change subscripts. Once we figure out what the subscripts are in the products, they are now off limits. Okay? All right, so let's just jump into examples. All right, I have 2 today. So first one, I'm doing the same thing as I did in the precipitation video where I'm giving names and I'm giving you some practice working with names. We are mixing hydrochloric acid and sodium hydroxide. I'll note that this is dissolved in water. All right, so let's turn hydrochloric acid into its name. That's going to be HCl. If it's an acid, that means it's dissolved in water. Aqueous. Sodium hydroxide, Na+, is sodium cation. Hydroxide is OH-, so we put those together. NaOH, aqueous. So this and that will be our reactants. All right, now we can write out the equation. And notice how I write these. I like to leave room on the left of each chemical formula for any potential changes in the coefficients. Remember that when you write a chemical formula, the default in front is a 1, but we don't write 1s in chemistry usually. All right, so this is double displacement, which means we're going to have to figure out the products through a swapping of the anions. All right, and we can't just simply swap up here like I showed in the previous video with precipitation. Double displacement reactions, we have to consider how to make each product neutral. So I'm going to write a list of ions on the side here. H+, Cl-, Na+, OH-, and I'm going to consider what other compounds H+ can make. I don't have to consider chloride because, well, it started with chloride. I don't have to consider sodium because they cannot form a compound. They're both positive and they'll repel each other. And then I'm going to consider OH-. They can form a bond because we have positive and negative. So we're going to make HOH, water, liquid. Same thing as H2O. but you're going to see in a minute I much prefer to write HOH instead of H2O when I'm balancing acid-base reactions. Hopefully I can make a case for why. And then the only other thing to consider is the sodium with the chloride. All right, so like you go outside, inside. That's a system I use for balancing charges in the products, predicting the products. All right. Now, it's at this point, some students might be getting a little bit of a wake-up call and starting to feel a little bit of anxiety, a little bit scared about where their progress in the chemistry course is at. I'd say this is when we're starting to like really get deep into reactions, this is sometimes a wake-up call. Maybe with the naming chapter, students will admit this to me. When it comes to their homework and classwork, they just kind of guess at the names, or on their homework they'll just look it up and type it in and trying to get that homework credit. And maybe you can get away with that. But here, for some reason, when it comes to balancing equations, students start to feel really exposed and vulnerable to where their chemistry knowledge is at or where it isn't at. Okay. So maybe the first red flag was I was able to turn names into compound formulas successfully there. If that was a struggle for you, I would consider maybe going back to those naming video tutorials to make sure you can bounce between names and chemical formulas in either direction, be able to do that successfully. You should be able to. I don't like making should statements in general, but I think here I kind of have to. You should be able to navigate the periodic table, know the general charges of your ions, like +1, +2, +3, +4, 3 minus 2 minus 1 minus 0. Have a little bit of knowledge about like type 2 metals, like iron can be 2+ or 3+, lead can be 2+ or 4+. And then knowing some of the polyatomic ions, like from my 343 polyatomic ion video. We talked about the oxidation state method and the 343 methods for learning those polyatomic ions. So feel free to check out my video on polyatomic ions or any other source, really. It doesn't have to be mine. But what I'm getting at is you got to know charges. You must know charges in order to do these problems. So consider this your official wake-up call. All right. So with that out of the way, I know my charges. I'm feeling confident. So here's my first product, HOH liquid. All right. And then I'm going to put in my second product. All right. So, this equation, you may have noticed, auto-balance itself. It balances itself automatically. That nice thing happens when every charge of all your ions are of the same, they're all the same number, just opposite in signs. Like we have +1, -1, +1, -1. All right, so it auto-balanced. But what if I'm going to do kind of the wrong thing here on purpose, just for learning purposes. What if someone wrote H2O here instead of HOH? Some students prefer this. They just like the look of H2O better. But just remember, though, when people see this, they may think, oh, both of the H's here came from the acid. And then maybe they'll be like, okay, I gotta put a 2 here. And then they're like, oh, I have 2 chlorines. Oh, I got 2 sodiums. And then they'll kind of leave it at there. Or maybe they'll get into a balancing equation like death loop, where you just kind of keep going and all the numbers start increasing. But this would not be correct, because in the haste of just going through the equation, maybe you forgot to notice that oxygen. And at this point, the way it's written, we have 2 H's, 2 more H's. We have 4 H's over here. And then we only have 1 oxygen there. So like the oxygens are we have 2 oxygens there. I'm having trouble explaining the wrong thing. But we have 2 oxygens there. If we have 4 hydrogens, and then we have 2 and then 0 there. So then you're like, okay, maybe I have to put a 2 here. And then maybe you'd get that right, but then you'd have to do the additional responsibility of balanced equations are supposed to be reduced to the most simple numbers possible. You'd have to divide everything by 2 in that case, and that's something that's easily forgotten. So do things your way, but hopefully I exposed my reasons for why I like to write HOH. Let me show this another way. And how I like to do this is with colors. So I'm going to use red boxes for all of my H pluses. And I will use blue circles for all of my OHs, OH minuses. All right. And hopefully through that, you can see we have 1 OH on each side. We have 1 H plus on each side. We have 1 Cl minus on each side. We have 1 Na plus on each side. So for me, this makes balancing jump off the paper way more easily when it comes to acid base. All right, and don't forget, when it comes to like many homework software packages, I suspect they will not accept HOH as water. So once you finish the whole thing, go ahead and change that back into H2O liquid when you type it into the computer. Okay, last thought before example number 2. Water must be marked as a liquid. Okay, you're not going to put aqueous for water because water itself is a liquid. You don't say water is dissolved in itself. Water is itself. Okay, perhaps we're going to have a philosophical disagreement here about that, but at the end of the day, convention is to put liquid for the water. Another way to think about it is if we put aqueous here instead, that would kind of suggest we didn't make any product, because the way we normally think about reactions is if everything's aqueous on both sides, you didn't make anything new. Okay, so another reason to mark water as the product, because you get the liquid. And again, some acid-base reactions, unless it gets extremely hot, you may not see anything. But grabbing the vessel, once you mix the acid and base, it'll often be warm from the formation of water. All right, one more example. And this one is a little bit funner. Funner should be a real word. Also, be careful, be suspicious. Beware, today's Halloween. Beware when a teacher says this one's fun. All right, so we got phosphoric acid and we have calcium hydroxide dissolved in water. We'll just pretend I had an AQ there all along. If it says acid, then by default it's aqueous. It means it's aqueous. All right, so this is the acid of phosphate. So phosphate's a PO4 3 minus. And we need to add enough H pluses to the acid to make it charge balance. And that's going to end up being 3 H pluses. So we have 3 of them. And so we go H3PO4 aqueous. And then for the calcium hydroxide, we have Ca2 plus for calcium. Calcium's right there. It's your 2 plus column, right? And then hydroxide is one of those polyatomic ions, OH minus. Okay. I haven't made a video. So I talked about phosphate in my 343 oxidation state method for polyatomic ions. I didn't use the Nick the Baby Camel method that exists on the internet. I find most of my students don't care much for Nick the Baby Camel, but for those who do, this is the Phoenix in Nick the Baby Camel. P is your starting atom. Central atom, you have 4 vowels, meaning 4 oxygens, and then you have 4 consonants, excuse me, and then 3 vowels, meaning a 3 minus. All right. So there's Nick the Baby Camel videos that exist out there. If you want me to make my own, I'm happy to do that. I've thought about that already. Okay, silly little rhyme trick out there to learn the polyatomics. Anywho, back to this H3PO4, and then we need 2 hydroxides, so that's going to be calcium hydroxide. All right, let's go ahead and build this equation. Okay, so that was a pre-step. If they tell you names, you have to do the pre-step of turning it into formulas. All right, and let's do some charge balance scratch work somewhere on the side. So we have H plus, we have PO4 3 minus, calcium 2 plus, and then hydroxide OH minus. It's acid base, so you're going to make a water and you're going to make an ionic compound. So there's our water, and let's make the calcium phosphate. All right, it's not as simple as just going Ca and then PO4 and calling it a day. All right, let me remind you that if it's not charge balanced, it doesn't exist, and you're writing an impossible chemical formula. All right, just like here, we wouldn't write H3OH2. That doesn't exist. All right, we're considering what's made when any H plus ions floating around bump into any OH minuses, and they have to be neutral. I know for some students, as I emphasize this, for some students, they need to hear this, and it's good to be reminded. And I know for other students, this is, I hate to use this word, but obvious. But so I thank you for your patience in advance. You were listening to this, and you're kind of like, duh. But I will tell you, it is definitely not duh for everybody. So let's keep that in mind. I'm trying to make this for a global audience. Hopefully, I'm able to keep everyone on board. All right, so back to this. We have 2 plus and 3 minus. I think this lends itself, whenever I see a 2 and a 3, I often think it's a great example to show crossover method. And in crossover method, you just turn the charge numbers into subscripts for the opposite ion. Now we have a polyatomic here, so we don't want 42 oxygens. We have to protect it in parentheses, so we have 2 phosphates. All right, so as a picture, 3 calciums, and then we have 2, 3 minus, phosphates. PO4, PO4. All right, so let's drop in that formula. And looks like we're running out of room. I should have wrote water first anyways. All right, let me pause this so I can rewrite it successfully. All right, that's better. We had water as our first product. And then we have the calcium phosphate as our second product. Okay, now in the previous example, we formed sodium chloride as our ionic compound, and like subconsciously, I put the aqueous there because table salt, being able to dissolve into water, you know, like you're making pasta or something, is a fairly common experience and learned pretty quickly. We know salt dissolves in water, table salt, but calcium phosphate, this is a good opportunity to refer to the solubility rules. In my precipitation video, I presented my way of teaching that. But the long story short from that video, aside from the ACE cards, the ions that are always soluble, is to know which ions are usually insoluble. And phosphate is a great example of that. Calcium phosphate, this is very chemically similar to our bones. And then, if calcium phosphates were soluble, then you'd have teeth and bones dissolving into your body. Anyway, so it's a precipitate, it's a solid. And I like to write down arrows on my precipitates, me personally. All right, so let's balance this. All right, I got some feedback from my previous lesson with the precipitation that some students are confused by when I write an inventory of ions in the middle here and keep track of everything on the left and right. Some people, I was a little surprised by this, pleasantly surprised. Some people find it easier to just look at the equation and just balance it like that. So I'm going to try that approach this time. Okay, what I usually recommend, especially on equations that look more complicated, as I look for my blue marker, there you are. There you are. All right. What I generally recommend in equations like this is to look for the most complicated thing. And I think this easily wins that award. Not just because it has a polyatomic, but more so because we have a 3-to-2 ratio. And here we just have 3-to-1, we have 1-to-2, and we have 1-to-1. And so this is the most complicated thing. All right, I'll get back to the idea in a bit. I'm going to put my H's in red boxes, H pluses, and I'm going to put my hydroxides in blue circles. There we go. So, back to the most complicated formula. Calcium phosphate. So, if I end up with 3 calciums, I need 3 calciums at the beginning. Now remember, once we've written our products, we're never going to write a subscript ever again, or change one. I need to end with 3 calciums, therefore I must have started with 3 calciums. So I put a 3 right there. This has the byproduct of making 6 hydroxides. 3 times 2 equals 6. I'll file that into the back of my mind. I want to fix the phosphate next. So I have 2 on the right side, which means I need to put a 2 here to get 2 phosphates on the left side, the beginning side. Okay? That has the side effect of creating 6 H pluses. 2 times 3, we have 6 of the red box H pluses. So I need 6 of this, and I need 6 of that. Well, now cure it. And just like that, we have a balanced equation for this acid-base reaction. This acid-base reaction is, I'd say, slightly uncommon. Most acid-base reactions in my teaching experience, you're going to have like a salt ionic compound that dissolves easily in the water. This is not the case. Here we made water and a precipitate both at the same time. All right, so hope this helps. I'm happy to do any other examples if people want. And if you have a better way of balancing equations, or maybe even instead of word better, like a different way, and it works for you more than the way I've shown things, or you think I'm missing something, yeah, let me know, and I'm happy to learn that and maybe share it out if I think a lot of people could benefit from that. So, but otherwise, again, thanks for watching, and next video will be net ionic equations. All right, thanks. Take care.